Let us start with the lecture number 4 of this module, robotic dynamics and control. Okay, robot dynamics and control. So let us see for like what we have seen in the last lecture. So we had a look at the actuators, okay, how to model the actuators and how to integrate the actuator dynamics with the robot dynamics, and finally we came up with a linear equation which was governing the system dynamics. Okay, it had a linear form with a nonlinear disturbance acting on it. Okay, you recall that form? So that is first thing that we did, and then after that we took that form and we developed some control algorithms basically for slow point to point regulation, okay, problems. Okay, so those control algorithms, we studied them, what is a steady state error, we did some analysis about that. Okay, now in this class we'll see, suppose we want to track a trajectory, what kind of control algorithms we can come up with using the same form for the equations of a robot dynamics along with the actuator. Okay, so we'll use the same form, but now we'll concentrate on developing some control algorithms for trajectory tracking kind of a problem. Okay, and then we'll have to see it will give you some improved performance over the previous algorithms, which are regulation algorithms, but still to improve the performance further you will have to go for a nonlinear control. Okay, the linear form of the equation would no longer give you very high performance kind of a control algorithms. Okay, so you have to study some part of a nonlinear theory, okay, specifically Lyapunov theory that we are going to see. Okay, so for that, we'll just build up our mathematical preliminary understanding for Lyapunov in the today's class. Okay, so let us start with the trajectory tracking problem. You remember this is our linear form with a disturbance for robot and actuator dynamics taken together. Okay, so you have this effective inertia and effective damping terms. Okay, this effective inertia, again recall that it is not a constant, we just assumed it to be some value which is averaged over the range of the motion of the manipulator. Okay, so it is a function of q in general. Okay, and then this B effective is a constant damping kind of a term, and then this is our control input which is going into the system. Fine, and then this is a disturbance term dk which accounts for all the Coriolis, centripetal, all those acceleration or inertia terms, and coupling terms in the D matrix. Okay, now we'll take a look at what is this trajectory tracking problem again. So we had our standard example of two link manipulator. Okay, recall that. Now trajectory tracking problem is to go from, you take the end effector from this point PS to this point PF, okay, in some predefined trajectory fashion. Okay, so in this case, say for example you are having a linear trajectory, going in a straight line from one point to other point. Okay, so that is a trajectory tracking problem. Okay, so in general you will be given this trajectory in terms of a end effector coordinate, how in the global coordinate you are given a path along which you have to go. Okay, and then that is your trajectory tracking problem. Now you do the inverse analysis, inverse kinematic analysis, to get, in this case, the desired joint angles. Okay, so this is joint angle for theta 1 and theta 2 for this particular manipulator. Okay, now these desired joint angles you want to then convert them into motor angles, desired motor angles. Okay, so this is the way you will find out desired motor angles by using the gear reduction ratio you know that there is a gear reduction from this theta 1 to like theta m1. Okay, so that using that you will convert the trajectory, the desired trajectory, into desired motor motion trajectory. Okay, and then that you will use for the trajectory tracking problem in this equation. So now you have this equation, and you want to have your theta m, theta motor position, to follow the trajectory defined by theta d m. Okay, so that is your trajectory tracking problem in the mathematical sense. Now we'll see. Now we have seen already this PD and PID control techniques. Okay, they are for the regulation problem. Okay, now what if we apply them for this problem? Can we apply them in the first place? And you will find that if you apply this PD or PID control for trajectory tracking problem, it will not work. Can you think about why it will not work? Just think about why it will not work. So in general, this regulation kind of a control algorithms, PD, PID control algorithms, they will not work here for the tracking case. No, overshoot, we can have a gain tuning such that like there is no overshoot, zeta is equal to 1, critical damping case. But the problem is that now you imagine, you see this response. Okay, this is your desired position. Okay, the actual response in the regulation problem, where you have point to point motion, is something of this sort. Okay, now what is happening in the tracking case? This theta d is no more a constant. Okay, it's actually varying. Okay, this theta is actually varying. So like for this motor response to catch up with theta d in very short time is not possible. So just PD or PID kind of a control, it will not work because of this reason. Because we are talking about a tracking problem now. Okay, so that kind of a control algorithm will not work here for the trajectory tracking kind of a problem. Okay, so what is a solution? So we see like why this is not catching up, because the disturbing terms which are this inertia and the damping terms, they are not in some sense fed forward in the control law, which is this. Okay, so what we can do is we can estimate what are these terms along the trajectory, and then that estimation we can compute and then put in our control. Okay, because we know that it has to overcome for a given trajectory, whatever is theta md, we have to overcome these forces. You know that there will be inertia force corresponding to J effective multiplied by theta double dot md. Okay, and B effective multiplied by theta double dot md dot. Okay, so that those effective forces, if we pre-compute and fed in our control law, then it becomes a feed forward control. So this is a block diagram of our standard PD kind of a control. Now we compute this feed forward term. This is a feed forward term based on the theta d desired motor position. Okay, and then that becomes our total control law. Okay, the rest of the part like this system dynamics or actuator and robot dynamics taken together, these three parts will remain the same. Okay, now let us see what is this. This is a control expression. You have this PD part, and then this is a feed forward term here. Now let us see what does it mean in the mathematical equations. Okay, to explain again why we use feed forward term, let us see. Suppose we have we have this equation and we are not using feed forward term. Okay, we have just PD control. Then we know that if this PD control is acting in such a way that it is whatever error is getting multiplied by proportional gain. Okay, and that error is produced now because of these dynamics and your decay dynamics. Okay, you understand that? Okay, you agree with that error will be produced by this dynamics because of the J effective and B effective terms and this decay part, which is the disturbance term. Okay, now suppose now we know that when we track a desired trajectory, suppose there is no error, then already we know that the term corresponding to J effective multiplied by theta m double dot d and B effective multiplied by theta m dot d, they are already known that this much of torque we have to overcome. So why rely on your just PD error kind of a control strategy? Why not feed these terms a priori? Because we know we have to overcome that part. So that's why we use this kind of a control law. We feed forward control law. Okay, so then that error will be reduced, and then you will see now when we do the analysis how that is happening. Okay, so this is our controller and this is the control expression. Next we will carry out some analysis of this controller and see what we get for a tracking trajectory error, like error in tracking the trajectory. Okay, so tracking trajectory error dynamics or dynamics of error in the following of the desired trajectory. Okay, so now what we do is you substitute this control expression that previously shown in the system dynamics. Okay, and then you will get this expression. Okay, now this is a feed forward term, and then this is our normal PD term, and then this is a disturbance term that is already there in the dynamics. Okay, so now we will define the error in tracking. This is a function of t, you can see here. Okay, as theta m minus theta d m. Okay, so then we will get this as our tracking error dynamics. Now you notice here that given this disturbance to be equal to 0, you will find that this is kind of a standard second order spring mask type of a system. So we can always choose this KD and KP gains to have this error going to 0 with whatever settling time we need. Okay, so last lecture we have seen already how to do these computations for KP and KD gains. Okay, for a given like type of a response, like if you want to move fast, how will you define omega, and from omega you will get this KP and KD for the system. Okay, and now you see that the tracking error is only due to this decay term, the disturbance term. Okay, more specifically decay multiplied by RK term. Okay, so basically now only the disturbance term is remaining. The immediate solution now is that to reduce the error further in tracking, you compensate for this decay term by pre-computing it. That is immediate logical thing that comes into mind to do, right? So next we will do that, and then see that becomes our computed torque kind of a control strategy. Okay. So again our linear form of equation with disturbance looks something of this sort. Now our feed forward control, the block diagram can be given in this fashion. Now we have to add the computed term corresponding to these, so this becomes something of this sort. You recall what was your decay? So this is a disturbance term, decay. Remember this J not equal to K, all the coupling terms in the inertia matrix, then Coriolis and centripetal acceleration terms, and then your gravity term. Okay. So this multiplied by Rk will form this computed term, and then you will find now that your error will, like error in tracking, will further go down, or you will be able to achieve faster tracking. I mean faster in the sense like the actual motion will converge to the trajectory faster. Okay. So in the transient period, that period also will get reduced because this reduction in the error. Okay. So what we will get for the controller is now the total this expression. Okay. So you observe that now we have to compute this term, and we have to compute in addition these terms. Okay. Notice that they are all functions of the desired trajectory, okay, which we know, like a priori we will know what is our desired trajectory that is to be followed. Okay. So this can be computed. Now the total computation will look like this of entire control law. The important thing to note here that like we have to have this lot of computations done for this control law. Okay, as we see here. Now system dynamics with this, now we can substitute the control law and find out this system dynamics, and you will see that now this decay term, previous term, has reduced by this amount. Okay, so it will be decay minus decay desired. Okay. So in general you have, once the transients are gone, the error between the trajectory and the actual motion will be lesser, will be very less, and because of that this term will also be very less. So that's how like you can manage better trajectory tracking in this case. Okay, but this is also not perfect, like you have not guaranteed zero error in tracking. Okay, it works very well for practical systems, I mean there is no problem, but still like theoretically some betterment of the performance can be done. Okay, the main advantage is that this error gets reduced, but now what is it at the cost of? Why the error gets reduced? You have to pay for something, like so when you are talking about reduction in error, you have to do all these control term computations like nonlinear, Coriolis, centripetal, gravitational forces in this D term, they have to be computed. And then computation means like, see, you remember like you have a sampling time in which you have to implement this control law in the digital domain. We have seen in the fundamentals of control that like there is a sampling time issue. So here like if we have to do these computations, we have to finish off within one sampling time. Okay, so that means like if we are not able to finish off, we have to use a faster microcontroller to compute. Okay, so like that is the additional cost that we are paying to reduce the tracking error. We have to do this computation, okay, and then compensate for this D term and get our tracking error reduced. Okay, do you see that? Okay. Next, we have not done so far any formal nonlinear analysis. We have been working in the mostly in the linear kind of a domain. We have seen intuitively how these PD control algorithms are good to reduce the error, and then like now we have seen how to extend that further for the tracking kind of a problem, okay, by pre-computing some terms which are there in the equation. So next we will study little bit about Lyapunov theory, which is a nonlinear analysis and design technique. Okay, and there are several nonlinear analysis techniques that are available in the literature. Okay, but we will not be able to cover all them in this class or in this course of robotics. We'll touch upon many important of them though. Okay, so Lyapunov theory forms a very important domain of nonlinear control tools, specifically for robotic kind of applications. Okay, so we'll study some fundamentals about Lyapunov theory right now. Okay, why we should why we should study Lyapunov theory? What it enables? It enables the analysis of any nonlinear system. Okay, and you know from robot dynamic equations that they are highly nonlinear in nature. They will have all sin theta, cosine theta terms or square terms of the velocities. Okay, so in general these equations are highly nonlinear in nature. Okay, and then also this theory helps you synthesize like many different controllers, okay, to improve or enhance the performance more than the what linear theory can achieve. Okay, so you can improve the system performance more than what linear domain tools or linear controllers can achieve by doing the true nonlinear analysis. Philosophically, if you see all these linear or nonlinear things, they are approximations to what is a real world. Okay, in the real world the systems are nonlinear in nature, highly nonlinear in nature. When you say the system is linear, you are making the linear approximation on that nonlinear world. Okay, and doing all the analysis for the sake of understanding more or designing better some controllers for your system. Okay, when you say nonlinear, now it is little bit better approximation to the real world, but again it's not capturing the entire gist of the real world itself. Okay, you should have that philosophical understanding at the back of your mind. When you say nonlinear systems, it is a better approximation than the linear system approximation to any of your real world systems, but it's not the end. Like actually you have like always you'll have some room for improvement. Okay, but like when you go for the nonlinear models, the like control analysis becomes difficult. Okay, it's not as simple as a linear domain analysis. Okay, so you have to study a couple of tools. You have to get equipped yourself with these tools to really do the analysis for the robotic manipulator cases. Okay, so let us see two things today. We'll study some mathematical preliminaries, and then we'll see some notions of stability which are not there in the linear domain. Like when in the linear domain you have either stability or system is not stable. Okay, but when you go for the nonlinear domain, you will have different notions of stability. So we'll see one or two of them here, so as to get you a feel of that. But there are many different notions which in the interest of time cannot be covered all them in this class. Okay. So first important understanding is what is called as locally positive definite function. Okay, LPDF function. Now understand the way this function has been defined, here this function v is taking some element of a real line, positive real line, and some element of this vector space Rn, and producing an element which belongs to a real line again. So this v is a function of, say, some time t and some state x. Okay, so v is a function of time t and state x. X is belonging to this vector space Rn. Okay, and v is producing a number which again belongs to this R, or it is producing a scalar number in simple terms. Okay, now it is said to be a locally positive definite function if it is continuous, and then v of t comma 0, like when x is equal to 0, you will get a 0, no matter what the value of t is. Okay, that is important. Like, no matter what the value of t is, when x is equal to 0, you will get v is equal to 0. And now there exists another constant r, is a positive constant, and a function alpha of class k. We will come to this definition, what is a class k function, very soon, such that this v is always greater than or equal to this function alpha of norm of x. So there is another new concept here. What is a norm of x? So we will see some of these concepts and the definition of class k function in the next slide. Okay, now this is our condition. So let us see first what is this norm. The concept of norm is very similar to what we talk about distance in our geometry. Okay, so if you are given 2 points in the space, how do we find distance? It's basically square root of x square minus y square. Okay, so x and y are basically defining these 2 points in a vector form. Now we have from the origin, this norm is a distance measured from the origin. Okay, so you can have this kind of a concept, like, I mean, this is like just to give you just intuitive feel about what norm is. So this is specifically 2 norm, like x2 is given by this expression. Okay, so this is our true distance concept, but in general in the n dimensional space. This is not 2 dimensional or 3 dimensional space, it can be n dimensional space depending upon what your n is. Okay, so that is a concept of norm. Now class k function has these properties. It is first continuous, then it is strictly increasing, okay, and then positive for x other than 0. So all these places where x is not equal to 0, it is positive. So it has this kind of a nature, and it is 0 for x is equal to 0. Okay, so this is a point where x is equal to 0, so this function is 0. And now what this condition means, alpha of x, alpha of norm of x is less than or equal to this v. So v is some function which can lie only on this side of class k function. Okay, it is always greater than the class k function of this norm. Okay, you see this is plotted against the norm of x. Okay, now this definition says that it is for all x belonging to this ball of radius r. Okay, now in general this ball will have, like, in the 2 dimensional it will be a circle, in 3 dimensional it will be a sphere, and in general in n dimensional it is hypersphere. Okay, so here in 1 dimensional you can like put that limit as r over here. Okay, so see this number r, the norm should be less than that number r for x to remain in the ball of radius r. Okay, so norm of x is less than or equal to r. That is a condition mathematically when you say that x belongs to this ball of radius r. Okay, so x should be less than or equal to this r. So beyond this line you are not interested like what happens to the function. The function may go below class k function, it may even go 0, go negative, whatever, you are not worried about that. But as long as you are saying that x is belonging to this ball of radius r, the function has this condition satisfied. Okay, so that's why we are calling it as a locally positive definite function. You cannot have it everywhere, it's some local domain which is defined by this value r or ball of radius r. Okay, you understand that? Now let us see next definition, which is positive definite function. Okay, now we have this similar definition, a function v taking some value in r plus domain or positive real line and some value in this Rn vector space to r is a scalar valued function. So you can call, in other words, v as a scalar valued function of a scalar and a vector. Okay, so this is said to be positive definite function or just PDF if it is continuous. Again the same condition, v of t comma 0 vector. Okay, you notice that this 0 is a vector, 0 vector, it gives a scalar 0 as the output of this function for all t values. Okay, and then there exists this function alpha of class k, again the same function, which where it satisfies now this condition, and this condition is also again the same condition, but it is holding for all x belonging to Rn space. Now it is not restricted to a ball of radius r now. Okay, it's everywhere, all whole of the Rn is included, or in other words, like that small r in the previous definition is taking value infinity. Okay, so it is everywhere now, this function is positive. So that is how this definition of this positive definite function is. So you can have now here in our same picture, we can see that this v will never come below this class k function. Okay, it will always be above that function, since the condition is valid for all x belonging to Rn space. Okay, now let us see some examples that will clarify this matter a little bit more. Okay, so we have first function, let us see whether now you can do any analysis to tell me if it is a positive definite. What we have to do is to verify these three conditions. The first condition, is it continuous for this part, like this v1, it is continuous. Okay, second condition, if you substitute 0 for x1 is equal to x1 and x2, so x1 is equal to 0, x2 is equal to 0, this is going to give you 0, and no matter what the t value is, it is always going to be 0. So that second condition is also satisfied. And the third condition is whether it is satisfied or not. See, this function itself is a class k function. Okay, it's always positive no matter what. Okay, so for x not equal to 0, this is positive and strictly increasing. Okay, for more higher and higher values of x, the function will take higher and higher values. Okay, so it is strictly increasing function. So this is indeed a positive definite function. Okay, and this is a positive definite, not just locally positive definite, because this is valid. Whatever these conditions we have seen, they are valid for all x. Okay. So now let us come to this function. Here we have x2 square, x3 square, and x1 raised to 4. Okay. Now similar to this part is positive definite. Now this part x1 raised to 4, is it positive definite or not? It is, right? You can see that. So and then this x here is given as x1, x2, x3. Okay. So this x vector is having all these x1, x2 and x3 terms, and this function is also having x1, x2 and x3 terms. Okay. I'll tell you why I'm saying that specifically in this case. So we have this result for this function again, that it is a positive definite function. Now let us come to this function where our x is specified as this. Okay. So it contains x1, it contains x2, but it is not containing x3. So you see which condition now gets violated here. Second condition will get violated. Okay. So v of t comma 0 will be 0, but it will not be that, it will be 0, like if you have x other than 0, still you will have v to be 0, which is not valid. Okay. So for any value of this norm of x somewhere over here also in this diagram, you can have v to be equal to 0, because if you have some vector like this 0, x2 is equal to 0 and x3 is equal to some value, the norm will turn out to be some value over here, and the function v is 0, which is violating the condition on this function condition on v, which is the third condition. Okay. So the third condition will get violated, not the second one. Okay. So this is not positive definite function. Okay. You see that this is very important understanding, very important, like you should never forget this understanding. You will find that your Lyapunov functions, when you do the analysis, you will use this PDF functions for Lyapunov theory analysis. So we will see at that time also, I will tell you, but this is very important understanding for when a function does not contain some terms, okay, then it cannot be a PDF function. Okay. So it should contain all the like components of your vector x. Okay. If one of the component of vector x is missing, okay, then the function cannot be a PDF function. Okay. You see that? Now let us see some other definitions. You see, the first definition is something called decrescent. The function is said to be decrescent if there exists a constant small r greater than 0 and function beta of class k such that v is now less than or equal to this beta. You remember the previous condition for alpha function, v was greater than or equal to alpha, and now this v is less than or equal to this beta function of class k. And again, now this is either local condition or it can be a global condition. If you restrict x to this ball of radius r, then it will become a local condition, and if you do not restrain x, then it is globally decrescent or locally decrescent, you can say that. Now function v will be radially unbounded if again our condition on alpha, like with alpha function, is satisfied. Okay, v is less than or equal to, v is greater than or equal to this alpha of class k, and this condition is valid for all the domain that we are talking about. Globally it should be valid. Okay, for all x belonging to Rn the condition should be valid, and then for some continuous function alpha with additional property that alpha of R will tend to infinity as R tends to infinity. Okay, so the function alpha should go on increasing as R goes on increasing till infinity. Okay, so that's how it is called a radially unbounded function. This is the radially unbounded function. Now another definition, V is locally negative definite function if minus V is an LPDF function and a negative definite function if minus V is a PDF function. Okay, so locally, I mean, like negative definite function, again locally and globally it follows just a negative of PDF function. Okay, so this is another definition. So let us we'll see later how we use these definitions for our analysis purpose, but just have a patience to just see these definitions and understand them carefully. Okay, later on we'll use them for robotic manipulators. Okay, now this quadratic functions, let us study a little bit more about these quadratic functions. Why we have to study them? Because they are very popular functions used in the Lyapunov theory. Okay, especially theory applied to robotic kind of applications. Okay, this you will find that these functions, quadratic Lyapunov functions, they are very popular. Okay, and then now let us see what is a quadratic function. This quadratic function can be written in this form. Okay, you understand this form? You have power or degree only 2 here, not more than 2. Okay, it's a polynomial kind of a function, and then you have these terms coming in cross coupled way and then square way. Okay, so like this can be represented in the matrix form in this fashion. You see that? Remember, your x is a vector or your state. Okay, x will consist of x1, x2, x3 up to xn components, where n is a like typically degree of freedom, number of degrees of freedom, or number of degrees of state equation, number of state equations, whatever. So x has n components. Okay, x belongs to Rn space, speaking in pure mathematical terms. Okay, and then this A is a matrix given by this expression. So A is a symmetric matrix. You can see that the element A12 is same as element A21. Okay, so because of this term 2A12 x1 x2 comes here. Okay, so given this kind of a matrix, you should be able to write this quadratic form expression, or given any kind of a quadratic expression, you should be able to convert it into this form x transpose Ax. Okay, so it is very easy to do that. Actually, you just need to look at the coefficients multiplying x1 square, x2 square, and coefficients multiplying x1 x2, x2 x3, and x1 x3, this kind of a terms, and then like you divide these terms, these coefficients of these cross terms by 2 and put them in the appropriate place in this matrix, and then you construct this matrix A. Okay, this is how you go about doing that. Okay, now next we will see how, like suppose we want this quadratic function to be a positive definite function. What are the conditions? Okay, so this is a theorem. We'll not see the proof of this theorem, but I'll just tell you this theorem and explain you the theorem. the quadratic functions are positive definite functions if the determinants of successive minors of A are all positive. Okay, so you have this matrix A, you take its first minor, okay, it will be formed by only the first element A11. Determinant of it is just the magnitude of this element, okay, it should be positive. So this element should be positive basically, it's not a magnitude, is the determinant is this element itself. Okay, now let's take the next minor. Okay, it will look something of this sort. So now you take the determinant of this, it will be A11, A12, A11 multiplied by A22 minus A12 square. Okay, you check whether that is positive. Like that, all you find is all these successive minors and see whether they are positive. If they are all positive, then it is guaranteed that your quadratic function form is a positive definite function form. Okay, so this is how you verify whether a function is positive definite or not. Okay, there is another condition also for verifying whether the function is positive definite function or not, based on the same matrix. It is in terms of the eigenvalues. You can see this theorem. These quadratic functions are positive definite functions if the eigenvalues of A are all positive. Okay, so you take this matrix A, find its eigenvalues and see whether they are positive, and you conclude about the positive definiteness of the quadratic function which is formed by using this A matrix. Okay, so this is an important understanding about the quadratic functions being positive definite. Now let us see some notions of stability in the Lyapunov sense. Okay, Lyapunov has defined different notions of stability, and let us try to understand a couple of them. So first of all, now stability in Lyapunov analysis is a characteristics of the equilibrium. Okay, in general the system x dot is equal to fx. Okay, this is a like a nonlinear system. Here we represent it in this form. Okay, so if you have x double dot coming into your any of your equations, you can convert them by using the state transformation. Okay, you introduce one more state, x dot is equal to say y, and then you transform it in this kind of a form. Okay, so that you can represent that system as a first order nonlinear differential system of first order nonlinear differential equation. Okay, this is possible for all the robotic manipulator systems, like they can be put in this form. Okay, now the equilibrium of the system will be obtained by solving for x. When you substitute like f of t comma x, this term is equal to 0. Okay, so this is a now 0 vector, this f is a vector valued function, this is a vector, so because your x is a vector. Okay, so by substituting here this equal to 0, you will get all the equilibriums of the system. There can be in general many equilibriums for a given system. Okay, then now you can do some transformations, okay, to make the equilibrium, like say you transform the variables so that your system equilibrium is 0 always. Okay, so our assumption will be for these definitions will be that your system has an equilibrium at a 0 position. Okay, it's just like you have to shift the origin of your x1 x2 up to xn to appropriate place, and then you will have 0 as a equilibrium for the system. Okay, it is always possible to do that transformation. So it is possible to do like that transformation for each of the equilibriums. Okay, and when we talk about stability, we talk about one of such equilibriums. Like for every equilibrium, there will be some kind of a different stability possible from Lyapunov analysis. Okay, so you should remember that the equilibrium, like the stability, is a characteristics of equilibrium of a system. So that you should remember. Okay, I repeat again, it's a stability is characteristics of the equilibrium of a system. Okay, now This is a definition for stability in the Lyapunov sense. So, equilibrium 0 of the system x dot is equal to f of x t is said to be stable if for each epsilon greater than 0 and t0 belonging to r plus there exists a delta which can be function of epsilon and t0 such that whenever you start x0 is your starting position, okay, you consider any differential equation system, it will evolve from a given, say this is a differential equation system, okay, these are n ordinary differential equations, okay. So if I specify x0 and this equation for different values of t, we will be able to find out how the system is evolving, right, okay. So given x0 and this differential equation, you will be able to find out by solving this differential equation how the system is evolving, okay. So when x0 like your initial state starts in this ball of delta radius, then it is guaranteed that your solution to this differential equation, the norm of that solution is always less than epsilon, okay. So that is a definition of stability in the Lyapunov sense. Now let us see geometrically for say R2 space, okay, how this will look like. So you have this R2 space, you have only x1 and x2 here, okay. So here you are given epsilon, some epsilon number, so it will transform into, like suppose we want to say like the norm of x is less than epsilon, or norm of something is less than epsilon, norm of this x1 and x2 is less than epsilon, then it will then your x should lie within this circle, okay, defined by this epsilon, okay. Now given this epsilon circle or epsilon ball or epsilon hypersphere in general, okay, then you should be able to find another circle delta such that whenever your trajectories are starting in this delta circle, they should not, whatever their evolution is, okay, it is evolving like this and it will go on continuing, but it will never leave this ball of radius epsilon. If it is leaving, then in the sense of Lyapunov it is not stable, but if it is not leaving, then it is a stable kind of, and then that is valid for all such points in this delta neighborhood of the origin. So this, in other words, it means that if your system is at equilibrium and you perturb the system from the equilibrium a little bit, it will not go wild, okay, it will contain itself to some limits, okay. That is kind of a notion of stability. Now let us see what is the next notion. We have to define first like attractiveness to see what is the asymptotic stability. So we will see mainly these two notions like stability and asymptotic stability, and for asymptotic stability we will first need to understand what is attractive equilibrium. So equilibrium 0 is said to be attractive if for each t0 which is belonging to this r plus, there is this eta function of t0 such that when the ball when x0 starts in this ball of radius eta, okay, or this number eta, then whatever solution is generated is tending to 0 as t tends to infinity, okay. So any solution, if it tends to 0 as t tends to infinity, okay, then that for that particular equilibrium it is called an attractive equilibrium, okay. So if you are in the neighborhood of this equilibrium, if you now perturb your system from this equilibrium and the system behaves in a way such that your solution of the system norm of that solution goes to zero as t tends to infinity, then that particular equilibrium is called attractive equilibrium. So it is attracting all the trajectories. Wherever you start in the neighborhood, all the trajectories are getting attracted to this equilibrium. That's why it is called attractive kind of equilibrium. Okay, now if the equilibrium is combination of these two, it is stable and it is attractive, then the system is called, or the equilibrium is called asymptotically stable equilibrium. Okay, so that is the asymptotic stability notion. Okay. Now the next definition is derivative along the trajectories. This is pretty simple. So we have this v, again same as our previous v, and then it is continuously differentiable with respect to all its arguments. Its arguments are this time t and x belonging to Rn vector space. Then its derivative is defined by these. So this is a standard derivative. Only difference here is that we have used here del v multiplied by x dot, where x dot is equal to f of xt. So when you substitute this x dot is equal to f, which is corresponding to your differential equation system, then you are getting the derivatives along the trajectory. Okay, so geometrically we can explain it in the following way. You can look at a figure. So you have this v, say in the R2 space we are representing it. So you have this v as a function of x1 and x2. So it will be in general say some positive definite function, and then you plot a solution trajectory. Okay, the solution trajectory will be some function of x1 and x2. Okay, in the x1 and x2 space it will be some curve. Okay, so in this plane consisting of x1 and x2 axis, it will be some curve. Now this curve when projected on this v will look something of this sort. This is a solution trajectory. Okay, there is no time axis representation in this kind of a geometrical representation. Okay, we have not given importance to time representation. This is a representation only in the x1 x2 plane with v plotted on the z axis. Okay, so now the slope of this line, okay, or slope of this solution trajectory which is projected on v at a particular point will give you v dot at that particular point. Okay, that is a physical interpretation of the v dot. Okay, derivative along the trajectory, derivative of v along the trajectory. Okay, so in general the derivative of at this point will be along x1 direction and along x2 direction, but when you substitute your equation x dot is equal to f of x, that derivative becomes along this direction, along the direction of the solution trajectory. Okay, now this is how I can explain the question that has come, like how this can help us in doing the analysis. So suppose 0 is a equilibrium and your total energy is 0 at the origin and positive at other places, that is a positive definite function, and then you perturb the system from origin and observe this energy function, okay, or this positive definite function. Now depending upon these three possibilities for this function, you can have different conclusions about the stability of the system. Okay, so we will see this thing again in the tomorrow's class, but we will stop here right now. We will just close these other things we will see in the tomorrow's class. We will stop here right now. So to just summarize the thing, we have seen the trajectory tracking kind of a control algorithms, which are in which we included feed forward and computed torque algorithm. Then we saw some mathematical preliminaries for Lyapunov stability, and tomorrow we will see the same mathematical preliminary and then how they are applied to your robotic manipulators. Okay. So we will generate some high performance control algorithms based on this theory and then see their performance in the tomorrow's class. Okay.